Okay, good morning. So let us start the class. Let us resume the discussion that we had in the last class. So before I start the discussion, just any of you, can you give a couple of points that we have discussed in the last class? What are we discussing in the last class? Last classes. Hey there.
Yes, sir. Good morning.
Yeah, good morning.
So we have discussed about the calculation of gradients of inner layers, sir, which is nothing but the product of error at the rear end and the input at the front end. And along with that, we have also discussed computational graphs.
Yeah, very good. So we have seen how to easily compute the gradients at any layer of a deep neural network. Essentially, we have seen that a weight vector, if you want to find its gradient of a weight vector with respect to the immediate variable, that's the local gradient. So, right, we want to find the global gradient itself, right? So if you want to find the global gradient of the weight vector, that is the gradient of the weight element with respect to the loss function. Then what we have seen is it is equal to the gradient at the rear end. That is also a global gradient up to that. So, okay, do the loss function by the variable where we are. So into that's in some sense the upstream gradient. Okay, into the gradient of the local gradient is nothing but the input variable itself will come. Okay, so it's essentially the gradient at the rear end multiplied by the input is what the weight update. Okay, at any given weight element. Fine, that we have seen in the last class, right? So, and then we started discussing on the computational graphs. We have seen some examples for finding out the local gradients and global gradients using computational graphs. So we started taking examples that are more realistic or more similar to what we deal in neural networks. So this is one such example where there is a matrix W, which is C cross D. Okay, and then there is a vector X, which is D cross 1, and this is just the loss function. Okay, this you can consider in some sense, you can consider currently this as a algebraic function, which is J is function of W comma X or F is function of W comma X. And subsequently, we will see its relation to the neural network loss computations and so on. Okay, so any of you have solved this? Any of you started doing this or tried doing this? Formulating operational graphs? Yes or no?
Yes, sir, we have tried.
Very good. So what are the inputs now?
One is a matrix, sir, another is a vector, D cross 1.
Okay, and then between them, what's happening?
It's a dot product.
Okay, you can consider it as a product itself, matrix vector product. Either it be dot product or product. So it is the net value I can write, okay, which is equal to W into X. Okay, because W is C cross D and this is D cross 1, this net value is C cross 1, right? It's a vector. Is this fine? And how do I get J now? Or how do I get F?
It's a norm of that column vector.
Yeah, it is norm of the column vector. So what should be this element here? What should be this operation here? What operation should be here? What is the operation we should have here?
It's the square root of sum of the elements.
Yeah, it is just finding the norm square. Okay, so it essentially finds this, if we say J or F, okay, if we call F here, it's nothing but norm of, okay, net, a vector variable net and whole square. So if we expand it, okay, net 1 whole square plus net 2 whole square plus and so on up to where? Net
C.
Up to where? C whole square. Fine. So this is what we have as the forward pass. Fine. So now in the reverse pass, let us see, or in the backward pass, let us see. Let us write the gradients, local gradients. and then we can write the global gradients. So now what should we write first? Dou f by dou f, or dou z by dou z. Okay, and this is equal to what? 1. And what is what should we write here? What is the gradient, local gradient here?
Dou f by dou net.
Dou f by dou net. Very good. Okay, so and what is the dimension? What do you think dimension of this will be?
It's a matrix.
Okay, any other answers? Any other answers? Quick answers I need. Dou f by dou net, what is it? Is it a vector, matrix, or a scalar? What are the dimensions of it? Yeah, quick answer is required.
It should be a vector.
It is
A vector, sir.
It is a vector of dimension what?
C cross 1.
C cross.
Yeah. So late to give this answer. Fine. So this is C cross 1. What is the answer of this? Dou net by dou f by dou net. If I compute dou net by dou f by dou net, what it will be? See, f can be written as C. This norm square can also be written. In what way? Do you can you suggest any other way of writing this norm square? Net is a vector, okay, and net norm square can also be written as what? For finding derivative, what I want to find is dou f by dou net I need. Okay, I'm not very familiar using norm square and then finding derivative. So is there any other way I can write this? Net 1 square plus net 2 square plus net c square I need to get. In terms of vector operations, okay, this norm, how do I expand?
Net into net, net transpose into net.
Very good. Net transpose into net. Okay, so then this is this one and this is this one. Okay, you make the product and you will get the norm square. Now, net transpose into net dou f by dou net. What is the answer? F of x, where it is x into x transpose. What is the answer?
It's a net, sir.
Is it net? Any other answers?
Net transpose.
Net transpose. Okay. What is any other answer?
2 net, sir.
Huh?
It's
2 net.
2 net. Okay, fine. So the answer is 2 into net. The reason is x transpose y differentiation with respect to x is nothing but y, and x into y transpose x differentiation again with respect to x is nothing but y. Okay, so and this both are same variable here, so it will be 2 net. We have seen x transpose x dou f by dou x is equal to f of x equal to x transpose x and dou f by dou x equal to 2x. Okay, so a same thing happens. This is one way of doing. Other way, if you are not very comfortable with this, so if you want to find dou f by dou net, just take any one element of net. Okay, just take jth element of net. Okay, so then what will happen? Dou f by dou net j I want to find. What is dou f by dou net j? It is equal to what? Dou f by dou net j. Look at this. 2 into what?
net j.
Net j. Okay, and for all j this is valid. J equal to 1 to c, whatever. Okay, this is valid. Then this answer, this implies what? Dou f by dou net equal to
2 into net.
Yeah, 2 into net. This is other way of doing it. Okay, so you can do either way, but you can cross check also with one doing one way and then writing the result. Okay, doing both ways. Right? Fine. So given all this, now we want to write this as 2 net. Fine. Okay. So now what we want, dou f by dou x, let us get this first. So what should I write here? Dou
net by dou x.
Dou net by dou x. Okay, so what this will be? First of all, what this will be? Dou f by dou x. Dou x will be, is it a matrix or a vector? You should tell very quickly this answer. What dimension this will be?
It will be a matrix.
It will be a matrix. Very good. And what is the dimension of this?
C cross D.
Okay, because net is okay. W say we keep the vector dimension as the rows, so it is D cross C. Is it not? Because vector dimension as the like X along the column. Okay, you will get D cross C. And then what is the answer for this dou x by dou net? Dou net by dou x? Somebody can tell the answer?
W transpose.
W transpose.
Okay, we have seen this with element operations before. Okay, now let us write, say, dou x, dou f by dou w. Given this, how do I write? What is the answer for this? So any quick answer? So we will go like this, right? So I think this is too light. I hope you got the point. How do I write? Dou f by dou net, dou w, dou
Dou net
f
by
by dou f by dou net, okay, into dou net by dou x. That's all, right? And which is equal to what? W transpose into 2 into net, or 2 into W transpose net. That's all. So yeah, are the dimensions agreeing? This is
That
D
is dou
cross
f by
C,
dou x. Sir.
D cross 1. What you are telling?
It is dou f by dou x. Sir.
Like, sir, you wrote dou f by dou w.
You have written dou f by dou w written.
Oh, fine. Thank you. Yeah, okay. Right, very good. So that's what we have. So 2 into W transpose net. Okay, so like this. So now you can write dou f by dou w as well. So to write this, we should write here what? Dou net by dou w. See, we know that this becomes a tensor because W is a matrix and then net is. So there are two ways of writing. You write element wise and then write subsequently, or write only k dou net k by dou w. Okay, first, and then write subsequently the other things. Okay, so better just even further simplified version is dou net k by dou w j I we will write. Okay, and then we will write the whole thing later. So first let us see how to write. So dou net by dou w. What should I write? So first let us write this and then write the subsequent things. What is the answer for this? Dou net k by dou w j, if you want to write. What is the answer for this? You have seen before. What should I write here? Yeah, please fill this.
xi when j equals k.
Yeah.
One row k equal to j and x into I.
Right. All right. This is the element answer because this is a scalar. This is also a scalar. So if you want to write in terms of a vector, dou net k or dou net by dou wji, if you want to write, then one row vector, okay, k equal to j into xi, right? So we will write it here. So as I said, dou f by dou w when I want to find, this is a vector, row vector in some sense, this is a column vector. See, this is a row vector, and if we see this is a row vector, and this is the column vector. So what happens? The dou f by dou w comes as summation dou net k by dou wji, when I am writing dou wji, into what? Dou f by dou net k. Okay, k equal to 1 to c. In vector form, if we write directly, one row vector gets multiplied with this row vector multiplied with this column vector. Okay, so no need of writing summation. If we write element wise, then the summation explicitly comes and sits here. Okay, so now if we write this is equal to what? Summation k equal to 1 to r, if we want to write in summation, or if we want to skip the summation. Okay, 1 to c delta k equal to z into xi, right, into what? 2 times what? Net k. So what is the answer for this? Can one of you quickly tell? I want a simplified answer for this. This whole thing now I should write simply. Yeah, one quick answer is required now.
xi into 2 net j.
Yeah, xi into, very good, 2 into net j, that's all. Okay, if you just put xi this side, k equal to j only will be 1. Okay, remaining all 0, and this picks out net j, that's all. So dou f by dou wj is equal to 2 net j into xi, that's all. Okay, so now given this element wise solution for dou f by dou wj, what is dou f by dou w now? Here what we had after all this discussion is dou f by, okay, dou wji is equal to 2 into net j into xi. Okay, and dou f by dou w now is equal to what? Same thing we have done 3 times. Okay, so far 3-4 times. Okay, so now you should be able to tell.
2 into nets.
Net into what? X transpose. That's all. Okay, so W is what dimension matrix? C cross
C cross D.
That's all. Okay, you can see that. Okay, this is like this and this is like this. Fine. So this is how we can do. From here it goes to there. Okay, so now let us see how this computational graphs helps in neural network framework. Okay. This I have done before, but given this, what do you think this solution is corresponding to? We want to picturize what this is doing here. What is the problem that is posed here? A quick answer is welcome.
Minimization function.
No, that's fine. But what is the problem considered here? Loss function is equal to O minus T whole square. And then the O is what? Output here, which comes from a function f. And f is what? Working on a net. And net is what? W into x. Where is this setting or the framework for getting the output? Huh?
From a neural network.
That's all. Okay, this is a neural network framework. So you have x here, W here, and O here. Okay, and the ground truth T here. Okay, so given the ground truth T, the loss function is written as JR here L. Is equal to what? Half, norm of half is written, yeah, O minus T whole square. Right? And now what we want to find in this neural network? So this is a neural network now, or a single layer neural network without a hidden layer. Okay, so what is that we want to find in this now? What is our objective?
Gradients.
Yeah, gradient of what? Delta. Yeah. What we want to find?
Gradients of different weights.
Gradient of different weight elements. Okay, so we want to find delta W or dou L by dou W. Okay, or we want to find delta W Ji, each element, gradient of each element. Okay, why do we need this? Let's just to get an overview or a background for what we are doing again. Why do we need this delta J, Wj, and so on?
Minimizing the cost function, sir.
Yeah, minimizing cost function, fine. Why do we want to minimize the cost function?
Learning the weights.
Learning the weights in neural networks. Okay, for performing what? For linear classification. Okay, so we are now completely in linear classification only yet. Okay, because there is no hidden layer. Still there, even though if there is an activation function, is just a modulation. Okay, from inputs to outputs. Okay, there is no mixing after nonlinearity. So that means each output variable is just a linear function, just the modulated linear function. Okay, so now with these weights, what do we do in neural networks? How to update weights?
We have a learning rule.
Yeah, using a learning rule, that is gradient descent. Okay, so this is what we do for weight update. So this is the background in which we are trying to do the optimization or find the derivatives, okay, through computational graphs. Okay, so hope the forming computational graphs and then writing the derivatives. Okay, all this is clear to you. So I am not spending time on this, but I would say that since this is very important, okay, to see how neural network can leverage, learning and neural network can leverage from computational graphs. This is the must exercise you people should do. Okay, you can write all this. You can find out the derivatives, local derivatives, and then write the global derivative. Okay, using the computational graphs. Okay, so I leave this to you for exercise. Is this fine? Is this fine or not? Yes or no? Not even single yes. Hello? Hello, is this fine?
Yes, sir. You are audible.
Yeah, am I audible now?
Yes, sir. You are audible, sir.
Yeah, fine, good. So now let us see for a little more difficult problems or a complex problems. If we have a neural network of more layers, then what do you think we can do? Do you think still you will be able to apply computational graphs? Yes or no? Hello, you people are there? Hello?
Yes, sir. We are
Yes.
here.
Yeah, you people, are you able to hear me?
Yes, sir.
Okay. So assume that even if you have one layer or two layers, okay, you can still apply this computational graphs, okay, and then find the derivatives. So what is the advantage of using computational graphs while finding the derivatives? Okay, do you see any advantage in using computational graphs for finding the derivatives? Yes or no? Hello, am I audible first of all?
We are audible, sir.
Yes.
We need not use chain rules or back propagation. We can directly use the local gradient or
Right. That's
local
observation.
derivatives and
So So we can use the local gradients itself. No need to use the chain rule. Okay, that's one thing. Second thing is what? What is second advantage? Hello?
Don't know, sir.
Hello?
Yes,
Yeah, am I audible or not?
now you're audible.
Yeah, fine. So what are the other advantages of using computational graphs?
Don't know, sir.
Yeah, fine, good. See, if you want to do it in large scale, okay, so what essentially you need to define
Local derivative.
gradients for finding gradients. See, you have seen 3-4 examples so far. What are all the different gradients, local gradients that you should know to compute? To compute a global gradient of any deep neural network. Are there just a couple of constraint local gradients that are good enough to understand and code them and use them for finding any deeper neural network, gradient in any deeper network? Yes or no? Okay, are you following or not?
Yes, sir, we're following.
Yeah, yes. Is it clear or not, whatever I have discussed now? See, if you know how to find out gradient for some activation functions, okay. If you know how to find out gradient for some like functions like norm, difference, okay, and then e power minus or sigmoid or e power operations, okay, and 1 by x operation, and then this kind of matrix vector multiplications, couple of matrix vector multiplications and vector operations, is it not good enough to compute the gradient for any deeper network or not? So say if I couple all these different constraint small blocks, okay, different small blocks that span the whole gradient operation or finding gradients, they may be not more than 10 or maximum 15 or 20, right? So if I just understand how to find out gradients in these small blocks and code them, okay, as different subroutines or some gradient automate that gradient finding and call them whenever I require in a computational graph, okay, appropriately, then won't we be able to compute the gradient even for a deeper network or even deeper and much deeper networks? Yes or no?
Yes, sir, we can.
Yes. So the answer is the advantage of computational graphs is if you just learn the some of the constraint gradient operations, okay, using them you can compute the gradient even for any deeper network, because each deeper we know exactly which operations we will be using in that deeper networks, and many operations are repetitive. Okay, in every layer what happens? It only becomes w into x, h into w. Okay, and there is an activation function f of. Nothing else is happening. Only in the last you have some loss function. We will see some of the loss functions for which how to find the gradient. What are the constituent elements for finding the gradients, and learn them, or we write some appropriate gradient finding functions and keep them. And you can use that small constraint local derivative functions and call them for finding any bigger finding derivatives or the weight updates in any deeper networks. Is this fine or not?
Fine, sir.
Yeah. So one advantage is using local derivatives. Okay, we compute global derivative. Okay, second thing is, say with writing functions or automatic gradient finding subroutines for few constraint functions. See, all these functions are only one variable. It's not nested function. It is a simple function. Functions. Okay. We can extend computation to finding derivatives in any deep neural network. Okay, is this clear? Fine.
Fine, sir.
Yeah, fine. Okay, good. So now let us see some of the limitations of using the same procedure or finding the like weight updates in deeper networks. As we said, that is the second part of the discussion that we want to have. Even before that, let us see some of the other loss functions which we may use in neural networks and which will have complementary advantages. Let us take even a linear classifier. Since now we know familiarity of finding gradients, okay, we can easily define. So if we have any new constant function, we can easily define how to find its gradient and use it in a bigger computational graph anywhere. And then we can find the global derivative. Okay, so if we have even 10 branches coming out, we can find easily the gradient at any of the input variables. Okay, so assume that it's a linear classifier again. Okay, let us see different kind of loss functions. In the previous discussion, we had one loss function being the mean square error loss function. Any other loss functions did we discuss?
Binary
Any
cross
other
entropy.
loss function?
Sigmoid function.
Sigmoid function is an activation function. It's not a loss function.
Binary cross entropy.
Yeah, cross entropy loss function. So it can be either binary cross entropy or cross entropy loss function. So wherein if, say for example, O and T, both if I consider as, okay, O targets are Pi, okay, and then the Qi are the probabilities corresponding to the output variables, okay, at each different neurons, and then Pi are the target probabilities. Then what cross entropy maximizes is what? Can one of you tell? What? How do I, or what cross entropy loss is? Oh, since we are considering loss, it minimizes it. So what is that is? Yeah, what's that? Can one of you tell or not? Entropy, how does it define?
Pi into log Qi. Plus 1 minus pi into log of 2, 1 minus.
Right? So this is what it cross entropy is, but this is with which sign?
Negative.
Negative sign. Okay, negative sign. And I is going from 1 to C, because we find out this binary cross entropy, whatever I have written. And since you have actually C neurons here, okay, at each neuron, we want to see its probability, output probability QI matching with the corresponding probability. And this each output probability can be 1 or 0. Okay, so we want to see that if it is, okay, if that class is to be active, it has to be 1. If that class is not active, that means other classes are active. Okay, in that case, it has to be 0. Okay, so that's what we want to see, right? So this is cross entropy loss function. So we have seen two different loss functions. Now, what we want to see is we would like to introduce one more loss function. Okay. So let me also put this as loss. Okay. So with this, even with cost entropy loss, we can also use this loss function at the output, and we can find apply the computational graphs to find out the gradients. Okay, so that we will discuss subsequently, or I will give it as an assignment for you to do it. For a binary cross entropy with one output, let us first consider, okay, so as an exercise for today or a homework for today. So for now, what I do is I will introduce another loss function, which is also widely used or well known as Hinge loss. It is also known as multi-class SVM loss. See, why we are introducing different loss functions? What is the reason for introducing different loss functions? Which answer is required?
To get the right model which fits the data.
What is that?
To choose the right model which fits the data.
Not able to hear properly. Now you can tell. So, yeah, please repeat. I couldn't hear. Yeah, please repeat now.
All of them are
Two. Yeah, please repeat again.
competently distance fixed. So how they are updated?
Okay, somehow I'm not able to hear. Are you able to hear my voice clearly?
Yes, sir, it's audible.
Your voice is
Yes.
audible, sir.
Yes, yes. Okay. So any other student answer? Yeah, I request answer from any other student. Say, assume that we have a, say in some of the situations, one loss function may be more appropriate to use. Okay. And some other situation, another loss may be more appropriate. If we have essentially, if you want to minimize the loss, then I think this first say mean square error may be more appropriate directly in terms of not even mapping it to probabilities. Okay. If you want to consider them as probabilities and then minimize or maximize the probabilities, okay, minimize the loss of between the one probability matching the other probability. Okay, that's scale divergence loss or cross entropy loss. Okay, then we can use this kind of loss function. Or if you would like to use, say, when we have different outputs, what can happen is this cross and this hinge loss or multi-class SVM loss, what it essentially says is, it tries to put the score of the correct class higher than the score of the other classes. Okay, it doesn't see to match the output variables with the target variables. Okay, that's not the main agent or the aim of this hinge loss or multi-class SVM loss. Okay, what it tries to put is, say if we have S1 and then up to say SYI for a given sample Xi. So let Xi be a sample belonging to YI class. Okay, YI class, YI, let it be, say ith sample is what we are looking at. When I give ith sample as input, its label being YI can be equal to 2. Okay, YI can be equal to 2 or whatever. Okay, or 5 or whatever. If we have 10 class classification problem, YI ranges from, okay, any value from 0 to 1. Sorry, 0 to 10. So it can take any value from 0 to 10 or 0 to 9, sorry. Right? So YI is essentially a class label. And then Xi is, ith sample is Xi. Okay, so in that case, what this hinge loss tries to does is S of YI. Okay, the score for the YI class or the corresponding class should be greater than or equal to what? All other classes. All other classes means Sj for all j ranging from 0 to 9. Okay, 0 to C we will say, or 1 to C. Is this fine? Is this clear, whatever I have mentioned now? Okay, so it compares the scores of the correct class with respect to the other classes and tries to maximize the score of correct class compared to other classes, right? So if you want to do that, say each time the input sample keep changing. And when the input sample changes, the output score of corresponding neuron has to be higher than the other neurons. Fine. So we should formulate a cost function which does this automatically. Okay, for different input samples. Okay, that's what is being done in hinge loss or multi-class SVM loss. Okay, so now I need your suggestion and help to proceed here. How should we formulate the cost function? Okay, it's such that always the score of corresponding class is higher than the other class, scores of other classes. Okay, in addition to putting actually greater than SYI, greater than or equal to Sj, it also gives a margin. Why is this margin +1? What is this taking care of? Can one of you guess? If I put a margin here, what is that it is ensuring? This is implying what? I will write something here, but I need some answer from you. Say if I put SYI greater than or equal to Sj +1, what does it imply? Some answer is required. Okay, let us do one thing. From today onwards, what I suggest is you all, I hope you are writing your notes. So what I suggest is you scan your notes and send it to me. Okay, send it, upload in the Google Drive. Though it brings a good volume of uploads, let us facilitate through probably our TAs to do that. So let us put a folder there or somewhere and keep uploading your notes. So that actually what you can upload in your Google classroom account. Okay, so that we will see over a week. In sense, you can also scan and send over a week. That also is fine. But I want to see whether you people are participating in class or for writing the notes and so on. Okay, so that actually I will be at least ensured that you are essentially following the classes. Okay, so let us make that assignment and at least put some, probably I think I see that from Professor Ejnara sir class that practice is helping the students. And also it is a good check for the students as well as instructor how the classes are going. So I would suggest that from this class, probably from this week itself. So you are supposed to do it every week, and that whether you have uploaded or not, we may see or we may not see and evaluate whole of them. But globally, overlook of your uploads will be done, and some evaluation based on that will be there in your final evaluation itself. Okay, so let us take that also in terms of an assignment. Okay, so now what does this imply? SYA greater than SJ plus 1. What does this imply? This implies Bhavana, you want to tell? Yes, Bhavana or Sandeep?
I'm not sure, sir, but it might be ensuring that it's the farthest margin from all.
It is giving, it is ensuring. Yeah,
Hello, sir, am I audible?
yeah, yes.
It might ensure that the margin is farthest from all the classes.
Margin is?
It is located in exactly in between or far away from the classes.
Right, very good. So what it is trying to see is previously what we have seen, the correct label is just greater than the other, correct score is just greater than the other scores. Now if we add plus 1, okay, this is a margin that is ensuring that the score, okay, of correct class, so proper class is at least greater than 1 unit, okay, than all other class scores. Is it not? So this is essentially, it is ensuring that the gap between the scores is, okay, at least 1 unit. Okay, so this usually is also exercised in this last function. Score of correct class is at least greater than or equal to, okay, score of other classes or score of correct class minus score of other classes at least greater than or equal to 1. Okay, it is writing in another way, so that there is a margin greater than or equal to margin. Fine. So this gives a more confidence that we will put our samples exactly into the same class. Okay, if we put this too much, learning may be difficult. Say if we increase the margin, what is the consequence? The learning, because to bring that much margin, you need to appropriately adjust the weights and so on, so that the learning may be more difficult. So there is a compromise, how much we could put the margin. Okay, so assume that usually plus 1 is margin that is used. And with this, now we want to evolve with a cost function. So what we want to do is for ith sample, write the loss function for ith sample. That is, we want to see that ith sample is correctly classified. Okay, so how should I write the loss function now? So you given this clue, or we want to ensure this, how should I write the loss function is the next question. How should I write? Can one of you guess or give me some suggestion? Yeah, some suggestion for loss function. How should I write it? Sj plus 1, in other words, should always be less than or equal to, okay, Sya. Okay, so given this, what does this imply in terms of loss? Sj plus 1 minus Sya should always be less than or equal to what? less than or equal to
0.
0. Okay, so that means that it has to be, say, at the maximum it can be 0. Okay, that means to correctly classify, at the maximum it can be 0. So the loss function now, if I want to write with this, what do I write? So this itself I can call it as loss function. Okay, or sy minus, either way I can write. And then it at the maximum loss can be either 0 or okay, sj plus 1 minus sy. And this maximum of this, if I pick, that I will consider as loss function li. So how did I come with this? What I'm saying is, if this is negative, no issue. In that case, we have a good margin. Okay, then absolutely there is no problem. But in case if SYI is greater, okay, that means if this is positive, it means what? We are crossing, we are already going away with the, like this, this is not correctly classified. Okay. So then this, if this is positive, then this essentially leads to loss. Is it not? If it is negative, there is no issue. But if it is positive, that leads to loss. Correct? Leads to loss. And this loss has to be minimized. Okay. And if this is negative, we don't want to bother. In such case, we just consider loss equal to 0. Okay, so what essentially now how I define this loss function is loss equal to 0 if sj plus 1 minus syi is less than or equal to 0. Fine, is this fine or not? So in this case, anyway, there is a margin and the correct class score is higher than other class scores, so no issue. In the other case where we have actually this sj plus 1 minus syi is greater than 0, in that case, there is a loss. We have loss and we want to minimize this loss. And what is the quantification for this loss? Directly, this value itself is the quantification for this loss. Is this fine or not? Writing these two together is being written in this expression. Okay, that this implies Li can be written in single form or a single expression as maximum of 0, sj plus 1 minus sy. Fine. This is for all j varying from where to where? J varying from where to where? 1 to C. Okay, and I refers to what? Ith sample. Okay, I is ith sample. Loss we have written for ith sample. Yeah, yi is the corresponding label, correct label. Fine. Hope this is clear. If you have any questions here, please ask. Hope this is clear. Okay. So now what I assume is we have actually this neural network is defined. Now we want to use this hinge loss to be minimized. Okay, and we want to write again a computational graph for doing this. Okay, so for defining scores, we have W into X, and the loss is equal to, for ith sample, is equal to what? Maximum of 0, syi, sorry, sj plus 1 minus sy. Okay, this is working on the elements of S. Okay, please note that. Okay, now if I have many samples as inputs, then the total loss is equal to what? If I for all n samples, okay, the loss will be equal to what? Summation over Li. Okay, so this is the total loss, right? I want to minimize. Now we want to construct a computational graph for it. If you want to construct a computational graph, see what is new in this compared to what we already know. What is the function that is there? new function that is introduced, for which we have not seen how to find out the formulate the computational graphs. What is the function? Yeah, quickly you need to tell.
Last one.
Maximum or minimum.
What is that? Max function. Okay, so max function, if we assume that after some initial things, we finally got sj plus 1 minus sy or something. So instead of writing this much, let us assume that the net value is here. Okay, net value I write here is this, and then 0 is this side. The max function is defining between, okay, maximum of 0 comma net value. Okay, in that case, if I make a forward propagation, what is the what is the error? How should I write the error? Is the question. Okay, so that we will see in the next class, and then try to conclude the discussion on computational graphs. Okay, you will be familiar using computational graphs with any loss function now. Okay, for any neural network, feed forward neural network, or any other like optimization, mostly around the neural networks. Okay, so with that, we will conclude the discussion on the feed forward neural networks and on the computational graphs. Then we will see the second point, that is limitation of deep neural networks, training the deep neural networks. And then that will give us motivation for introducing another activation functions. Okay, and there also you need this max function. Okay, the ReLU activation function that we will define in the next class also needs this maximum computational graph with max function. Okay, we will see how to handle this. Okay, and then we will probably in the next class, we will conclude these details and move on to convolution neural networks. Okay, and then training and convolution networks. Before that, there are some implementation aspects which we wish to discuss on neural networks, we will discuss, and then we'll move on to convolution neural networks. Okay, so thank you then. So if you have any quick questions, you can ask. Otherwise, we will conclude. I suggest that from this class onwards, you make notes and then you are supposed to upload the notes. Okay, scanned notes in your Google Classrooms. Thank you.